Okay, welcome everybody. So for today's colloquium, we are very happy to have Miguel Montero from IPhT Madrid. Miguel is an expert on the imprints that the putative ultimate theory of quantum gravity might leave on its low energy description, and today will take us for a hike to the quantum gravity swampland. Please.
Okay, thanks very much, Carlo, for the kind introduction and for the invitation to give a talk here, and to all of you for being here. So indeed, the point of this talk is I'm going to tell you, so indeed I work on something called the quantum gravity swampland. It's a colloquium style talk, so it should be accessible for everybody. So indeed what I'm going to be telling you is what this thing is and why should you care? What is it good for? Oh, okay. But before I do that, there's a very important thing that has to be said right from the start, which is that since the point is to get a message across, you should interrupt me at any point, okay? With questions, comments, whatever, okay? The more questions there are throughout the talk, the better it is. So when Antoine wrote to me to give the colloquium, he wrote to me, he said the following. He said it's a very wide group, containing people doing string theory, conformal field theory, particles, cosmology, heavy ions, condensed matter, quantum information, lots of stuff. Research directions here are very, very broad. And so I'd like to start with a question. Who in this room thinks routinely about gravity when conducting your research? Please raise your hand. Okay, lots of people. Now, lower it if you're a string theorist or a cosmologist, or if you work in gravitational waves. Okay, so we have still two people who kept their hands up. That's good. But most people who are raising their hands, they lower it, and most people in the room, they just not raise their hand. And that makes sense. And that makes all the sense, because in most applications, gravity is such a weak force that is negligible, right? So for instance, you take two electrons, gravitational force between them, put at some distance r, is just this. This is the electromagnetic force between them. And if you look at what the ratio of them is, it's just this thing, it's 10 to the minus 43. Okay, so gravity is a very, very weak force compared to all the other forces that you care about in most areas of physics. Here I wrote the ratio in a nice way in terms of two length scales. One of them is the Compton wavelength of the electron, okay, which is some length scale which has to do with the fact that I was comparing the force in an electron. And the second length scale is this LP, which is the Planck scale. That's going to be an important player of the story, is the length scale that controls gravitational interactions. So indeed, gravity is very weak. And it takes something as big as a whole planet to generate an effect. And even then, just jump. And for a while, you're beating, just for a second, but you're beating a whole planet. Okay? So gravity is really a tiny force. So indeed, the gravitational effects in general are controlled by this Planck length, which is 10 to the minus 35 micrometers, which is tiny. You can compare it to the length scales of an atom, an Armstrong. Length scales of nuclei, 10 to the minus 15 meters. And the smallest length scales that we probe directly at LHC, if you're generous, you say that maybe you're probing things at maybe at 1 TeV, it's 10 to the minus 19 meters. Okay? So it's some 15 orders of magnitude away from this. So indeed, this length scale is much smaller than all the others. And one of the golden lessons, one of the things that you learn in the physics undergrad, one of the basic things, is that if you are studying a physics problem at some length scale L, then the answer to physics questions on that problem, it should be independent of whatever happens at the smaller length scale, little l. Right? This is sometimes called separation of scales, and it's a basic thing of science. Okay? It's very important. It underlies the fact that we can understand the world in a scientific way. Because it's thanks to the separation of scales that if you want to build a water mill, it's 300 before common era, and you're building a water mill, you need to understand something about water, but you don't need to understand atomic theory to do it. because the length scales, characteristic length scales of the water molecules is much smaller than the length scales of the watermill. So you're good to go. The same reason, you can do optics much before you have to develop QED. Because even though optics is some low energy limit of quantum electrodynamics, at very low energies, you don't care about this. Huh? And there's many, many more other examples for this. Questions so far? Yeah, this is clear, no? This is like a bit obvious thing, yes? Well, let's see. Let's see if it's so obvious. Now, it follows from this logic, right, if LP, the Planck length, is so much more than any other physical scale of interest, then I can always forget about it. So that's what you would guess, right? That's the natural thing to guess. However, the whole point of this talk is that things are more interesting. Let's say you're a heavy ion person. Is there anybody here from doing heavy ions? Okay. They are probably hard at work thinking at problems like this. Okay, so they're thinking about colliding their heavy ions like this. So you have two heavy ions, you collide them, and you ask what happens there. The experiment is not perfect really, and it's not perfectly aligned, so rather than doing a head-on collision, you typically do something like this. You have the two ions like separated some transverse length scale here, some B, this B is called the impact parameter, okay? But there's some transverse separations between the particles. And then of course, there's another quantity you have in your experiment, which is the energy of the particles E, essentially, right? So you're colliding the ions, and you can collide them at any energy and with any separation. So if you're if you're doing the experiment, you want to put the B and the E in such a way that you access some interesting physics you're interested in. But imagine this morning, it's a gray morning, it's a bit tired, so you're not thinking things carefully, and instead of putting the impact parameter to an interesting length scale, by some mistake, you just make it very large. Okay, so you just separate it. Let's say you make the impact parameter 1 meter. So the two particles are now separated 1 meter. Well, then if you do this, then it is not going to be very interesting as a probe of heavy ion physics, because the particles are not going to interact much. They're just going to pass right in front of each other. They're not going to interact strongly. And this is going to be the case no matter how high the energy is, right? So you can make them faster and faster. That's OK. They're far out, so they don't interact. And indeed, this is in some senses because physics is local, right? Like if the two ions are 1 meter apart, there's no way that one can communicate to the other, or not strongly. Furthermore, if there's any new physics, any short-range physics appearing at some new scale, let's say that if you probe the ions very closely, there will be some new physics controlled by some length scale here. So you need to probe this close to the ions to see the nucleus to see the new physics scale. Then you're also not going to see it because the impact parameter is very large compared to the scale of new physics. So this is the separations of scales that we're talking about, okay? And this is, kind of like common sense, right? It's like if particles just go through each other very far away, they don't talk to each other. But you can actually prove it rigorously in quantum field theory. If you have a quantum field theory which is UV complete, then this kind of behavior, that things at very high energies far apart from each other don't see each other, is a general feature of quantum field theory. Okay? Question so far? Is this clear? Good. So, in quantum field theory, if you have the two particles going far apart, let's say 1 meter apart, nothing's going to happen. Boring, right? That's the prediction of quantum field theory for this system. However, this is not what we believe happens if we do this in the real world. So you have the two particles going 1 meter apart from each other. So impact parameter B is 1 meter. And let's say that then you start increasing the energy. You start increasing and increasing and increasing and increasing the energy. In quantum field theory, again, they just go past each other faster and faster and faster. Who cares? But in the real world, once the particles get to the point of closest approach, if you think about it, at this point of closest approach, if the center of mass energy of the particles is very large, you actually have a lot of energy within, let's say, a ball of radius the impact parameter. Okay? Lots of energy means lots of mass. And if you think about gravity, that means that if the energy is high enough, namely if the energy is such that the Schwarzschild radius of a black hole that you would associate to the energy is bigger than the impact parameter, then these two particles are really within a black hole horizon, you would expect. So what you would expect is that these two particles actually collapse to a black hole. All right? Is that clear? It's just we're just computing the mass and comparing with the Schwarzschild radius. Now I asked, was this clear? And people were like, yes, this is clear. Like, okay, fine, it's like obvious. This is crazy. This is absolutely crazy. I mean, it's impossible in quantum field theory. We were just agreeing that particles just go through each other and they don't talk to each other. Okay? And it happens, for arbitrarily low, sorry, I should have said high, yes, large, for arbitrarily large impact parameter. Okay? No matter how far you put them, sure, you have to increase the center of mass energy, but they're not going to talk, in quantum field theory, they wouldn't talk to each other, and here they form a black hole. Okay? So even though you're looking at physics at very long length scales, gravity enters the picture, and you end up forming things like black holes. So there's some kind of mixing between high energies, black hole behavior, and long length scales that just doesn't happen in ordinary quantum field theory. Yes, please.
So in this configuration that you described, where the two particles are moving on each other like this, the system is also going to have a angular momentum?
Great question.
Which is going to modify the calculation of the shape of the Schwarzschild horizon, presumably? Could that alter the conclusion about whether or not they're going to actually be inside the horizon or not?
So certainly the black hole that you're going to form with more probability is going to be close to extreme Alker. That is true, right? And we were just talking about this, I think, with Carlo just before at the coffee break. I was asking him, like, is this, formation probability, like this formation is something that you would expect just from the heuristic argument I did with the mass? Is it proven rigorously? I think the answer is not so far. So yeah, indeed, you probably produce an extremal black hole, extremal Kerr black hole. It's not proven. It's something that sort of like is reasonable. You could look at other setups where it's a lot more, in fact, maybe a lot more reasonable, maybe even rigorous. For instance, you could imagine that instead of like colliding particles like that, you do S-wave collisions, right? Then, Birkhoff's theorem tells you that the moment that it really tells you that the moment that you have a lot of mass within the Schwarzschild radius, then that's inside a black hole. Okay? So maybe that's a setup where things can be done a bit more rigorously. Okay? I'm making no claim of rigor here. Okay? I'm just giving you the general flavor of things. Yeah. But this is true, you see, but I do want to make the point that even if they're very far, then you form the black hole, and indeed, then it's going to be a black hole with lots of angular momentum. Yeah. More questions? Okay. So, why did this happen? Well, in some sense, it happened because, we wanted to put states which have more and more energy, even though they're very far apart, but gravity couples to mass, couples to energy. So if you give energy to the particles, gravity is going to see this. In some sense, it's the equivalence principle of gravity. And it means that gravity, in some sense, in the deep UV description, as long as this property holds, cannot be a quantum field theory. It cannot be a local quantum field theory in the usual way. And so that means that the usual logic that we were describing before with the water mill and whatever and the separation of scales, in principle is off. And maybe, just maybe, gravity can tell you unexpected things at low energies. Okay? I mean, here it just did, right? The quantum field theory prediction was just wrong. So indeed, gravity can be important at low energies. At this point, maybe you're thinking something like this. What? No way. If I'm doing a PhD in condensed matter, is this guy telling me I should worry about quantum gravity for my condensed matter PhD? That's insane. Well, yes, I am saying that these things can matter for condensed matter questions. And they require a different way of thinking than quantum field theory. At the same time, the usual principles of quantum field theory work extremely well. So if there's any deviation from those, they have to be quite subtle, right? So indeed, you can probably ignore it day to day, but also you might learn something interesting from thinking about it. And indeed, what we found is that the most interesting effects that quantum gravity has at low energies is not so much in these regimes where you get like things which are very different from what you expect in quantum field theory, is that the same effects, the same logic, can actually give you constraints on the low energy quantum field theories that can be consistently coupled to quantum gravity. Okay? So to be more concrete, we believe that if you give me certain quantum field theory with certain masses or certain couplings, for some values of those masses or those couplings, because of effects like this, which I will spend the rest of the talk describing, you can couple it to gravity. They are okay as quantum field theories. They're perfectly fine quantum field theories. They belong to the Peskin and Schroeder textbook. But they're not okay when coupled to gravity. So if you draw this abstract picture of, this is clearly the space of all quantum field theories, yes? It's a blue blob. So each point, let's say some quantum field theory which has some masses, some couplings. And here's another point which has some other masses, some other values of the couplings. We believe that not every point here, not every point in this blue blob can be coupled to quantum gravity. They are fine as quantum field theories, but they don't arise as the low energy limit of a consistent quantum gravity. So we can divide it into two regions. One is okay with quantum gravity, the other isn't. And in the jargon, the region that is okay, that can arise as the low energy limit of quantum gravity, it's like the good theories, the nice theories. They form a beautiful landscape of theories. And what is the opposite of a beautiful landscape? A swampland. So the effective field theories that cannot be coupled to gravity are said to be on the swampland. So the basic idea, yes, this question.
You usually hear, oh, quantum gravity is not renormalizable.
Yes.
Can you put this in the context of what you just said?
Yes, yes, yes. So if you take an Einsteinian theory of gravity, right? So you're going to get at low energies a quantum field theory, right? Plus the Einstein interactions, they're going to be suppressed by the Planck scale, so that theory is going to be non-renormalizable. Because it's non-renormalizable, it's not obvious from the get-go which things are, let's say, UV completable to some, quantum gravity model which is unitary or has some other desirable properties, okay? And because of the equivalence principle, when you write this action for the matter coupled to the Einstein theory, you got to put the square root of G, right? So the matter couples to gravity. So there's going to be loops, and they're going to talk to each other, and so it's conceivable that for some choices of quantum field theory, once you find some UV completion that gives you this thing at low energies, then some choices of quantum field theory can never appear. Okay? Does that make sense?
Yeah.
Good. More questions? Good. So that's the basic idea of the Swampland program, is we want to find out what distinguishes the good quantum field theories that you can couple to gravity from the bad. Okay? We want to tell you what are the consistency conditions that you must satisfy to be able to couple the two of them. And that is interesting in itself. It's a surprising thing that maybe not every quantum field theory can be coupled to gravity. But furthermore, it's potentially exciting because even if finding what is the correct quantum theory of gravity in our universe might be very tough. But maybe, just maybe, some general properties can be used to connect with experiments to make predictions. So that's sort of the philosophy. That's sort of like the end goal of the Swampland program. Okay? So why is it called the Swampland? I told you already, it's because it's the opposite of the landscape. And the word landscape comes from string theory. Okay? So the Swampland program is very tied to string theory. So you might think, maybe there's just one consistent quantum theory of gravity, which is our own universe. But actually, that's not true. In string theory, we have constructed, it's a consistent theory of gravity, which has lots of solutions. And each of these solutions is a consistent model of quantum gravity. It's mathematically consistent. So whatever gives you low energies is in the landscape. So each of the solutions that you have from string theory at low energies looks like an Einstein theory plus a certain quantum field theory at low energies. And so the idea is that string theory gives us many effective field theories that are for sure in the landscape. So we can use these to sharpen the boundaries of the Swampland. So for instance, if we get an effective field theory, let's say, comes down here, then we know that we should extend the landscape here, and so on and so forth. Okay, so there's this interplay between the two. The idea is that the Swampland is more general than string theory. Okay, so the Swampland, true Swampland constraints should be coming from general black hole things, arguments like the ones we're discussing that are hopefully true in every quantum gravity. But it is true that there's a lot of back and forth between string theory and Swampland. Because if you have any proposal, you can check it in string theory, and maybe string theory can also suggest what is true in quantum gravity in general. Okay? So that's sort of like the idea. We have general principles, we can connect it. And so for any proposed property of quantum gravity that we believe is true, for any proposed Swampland constraint, one typically has, on one hand, general arguments based on black holes, kind of like the stuff that we were discussing at the beginning. And on the other hand, because these arguments are never solid, like fully solid, fully rigorous, and they cannot be because as of today, we cannot prove things in quantum gravity fully generally. We also check them in string theory. So if I tell you effective field theories coupled to gravity have to be such and such, then I can go to a million string theory compactifications and say, yes, that's true in my million of compactifications. Or no, here's a counterexample. Because we cannot prove things generally, they are called conjectures, right? But some of them have a lot of evidence. And so that's how the Swampland program is usually structured. We have different Swampland conjectures that tell us we believe quantum gravity has this property, or that property, or whatever. So what this talk is about, what we will cover briefly, is the story of the three main conjectures that have seen the most progress in Swampland in the last, let's say, 10 years. So those are the conjecture that there's no global symmetries in gravity, the so-called weak gravity conjecture, and the distance conjecture. Okay? So that's what we're going to do for the rest of the talk. Before we go on, are there any questions about the general philosophy of Swampland?
Maybe it's just doubt due to the examples that were a bit simple and now we're going to show us. I mean, for sure you're going to show us even more interesting things, but I guess in the first example you gave us in the relation between the gravitational force and the magnetic force, you introduced the h bar to define our length, but eventually h bar cancelled, right? Because you introduced
Yeah.
So that was not a state without quantum things in any way.
No.
And then, I mean, the confirmation, I mean, it is more subtle, but I guess you can cook up a simulation that
Yes.
about the simulation, which is purely classical.
Yes.
Produces a black hole. So, I mean, is it obvious from the get-go that we're going to actually learn about quantum gravity?
Right. So I'm going to give you next a heuristic black hole argument for these no global symmetries where quantum effects are going to be very important. Indeed, if I did not have quantum stuff appearing at some point, it would be very, everything would be sort of like you would get with classical reasoning. So for instance, this example, as you were saying, of the two particles colliding, forming a black hole, you can get from semi-classical reasoning in gravity. What I'm saying is that if that was just all there was, you would be able to argue that gravity just can never come from a quantum field theory, but it would be very tough to say that somehow that also trickles down to say interesting things about the effective field theory, right? So for that, you need a bit more quantum. So we'll see that in a moment, okay? More questions? Okay. So let's go learn our first Swampland conjecture. First Swampland conjecture is the oldest Swampland conjecture, and it says that there are no global symmetries in a consistent quantum theory of gravity. Okay? So to understand what this means, we need to understand two things. First, we need to understand what is a global symmetry. And second, we need to understand why is it a bad thing in gravity. So to illustrate what a global symmetry is, I'm going to do it through an example. First of all, a symmetry, global symmetries are associated to conserved charges in physical processes. And so here's a process which has two conserved charges. This is beta decay, so a neutron goes to a proton plus an electron plus an antineutrino. And there are two conserved charges in this process in the standard model. One of them is electric charge, is 0 on the left and 0 on the right, because these two guys cancel, proton and electron. And there's a second charge in the standard model, which is conserved by every standard model process, which is called B minus L, baryon number minus lepton number. And so here is 1, because neutron has baryon number 1. And here it also has 1, because proton has 1, and these two guys, sorry, I'm not very good at pointing with this. These two guys cancel each other. So these two quantities are conserved in the standard model. So quantum field theory has to conserve charges. But the two of them are very different. Right? The electric charge is coupled to a long-range gauge field. It's coupled to electromagnetic field. So that's a gauge symmetry. For a continuous symmetry like electric charge, you can say that having a gauge symmetry just means that it's coupled to a gauge field like electromagnetism. But really, the full invariant way of saying what is a gauge symmetry is something that satisfies a version of Gauss's law. Okay? So electric charge satisfies Gauss's law, and that means that you can measure it with the flux from very far away. If I give you a box, black box, and you don't know what is inside, and I ask you, what is the electric charge contained within the box? You don't need to open the box. From far away, you just compute the electric flux, and that tells you the electric charge. So that's a gauge symmetry. And a global symmetry is any other charge, any other conserved symmetry, that cannot be measured like this. Okay? So for instance, if I give you the same box, and I ask you how many baryons are inside the box, within the standard model, if you don't use physics beyond the standard model, you really need to go and open the box and count how many baryons are there. So the thing that's in the Swampland is global symmetries. That is, symmetries that are not coupled to a gauge field, symmetries that you cannot, charges that you cannot measure from far away. Okay? So that's what a global symmetry is. And fine, why is it forbidden? Well, I started the talk speaking about black holes colliding, and indeed that's the reason. It's forbidden because of black hole physics. So to see what is wrong with a theory with global symmetries if you have black holes, a theory of gravity, let's do by contradiction. So let's assume we have a quantum gravity which at low energy is some effective field theory which has some global symmetry. Let's call it B, and let's see what happens. Let's derive sort of like a contradiction or a problem. So I'm going to assume that I have some effective field theory coupled to gravity, where I have some charge B, and the charge B is B for blue because it counts the number of blue particles. And there is just one particle species which has some mass m. Okay, take it to be non-zero. So if I have this theory, I can do the following. First, I can take a large number of particles, and just like I was doing before, I can collapse them to form a black hole. Okay, so they form a black hole. And because I'm assuming that there's a global symmetry, by assumption, the charge is conserved when I do this. There's no way that the charge is broken. So I have my black hole, but then what happens? Well, here's where quantum effects enter into the picture. This thing, according to Hawking, is if this is, let's say, is a Schwarzschild black hole. Imagine that the collision was spherically symmetric, so we can only think about Schwarzschild. Then this thing starts evaporating. Starts evaporating, and you can actually prove, just from Hawking's calculation, it follows that the evaporation process conserves the charge B. Okay? On average, the charge is conserved. There can be little fluctuations, thermal fluctuations, but you can show they're much smaller than the B. So it's effectively, as on a first approximation, the charge B is conserved by the evaporation process. Okay, so this black hole has charge B0, keeps getting smaller and smaller and smaller, still has charge B0. And at some point, maybe when the black hole reaches Planckian mass, maybe some bigger length scale, it doesn't really matter for this argument. the black hole becomes quantum mechanical. Maybe you have some black hole which is roughly 1 Planck mass, and the curvatures are very high, and Hawking's calculation just breaks down. Okay? So at that point, you just got to say, look, I don't know what happens after this point. But if you follow these things, you actually, even if you don't know anything about the physics here, you can say something quite interesting about the object that you have created here, which is that this remnant of black hole evaporation can be absolutely stable. It's protected by kinematics. Why? Well, if the mass of the remnant has charge B0. If its mass is less than the mass that the effective field theory state with B0 particles will have, it just cannot decay to it because of conservation of energy, right? It would need more energy than the guy has to decay. So just by kinematics, it's going to be exactly stable. Is this clear? Yeah? Well, I see people saying, yeah, it's clear. Well, again, this is a problem. Because to make this argument, I didn't assume anything about the number B0 other than it was large. So I could have started with a cloud of particles with charge B0, or B0 plus 1, or B0 plus 2. In all cases, I can run the argument out to the black hole of Planckian mass. So I end up having one object which has charge B0, and has charge B0 plus 1, B0 plus 2. Keep running the argument, and you actually have infinitely many states, all of mass and Planck. This is crazy. Yes, question?
You sort of know that at least after page time, you cannot trust Hawking computation.
No. You cannot trust it for computing things like entanglement measures and stuff, but the effective field theory calculation works until the black hole leaves until the black hole becomes so small, effectively you don't trust. So computing things like entanglement entropies, you need to look at, essentially, for instance, if you look at the density matrix of the black hole with the radiation, you need to have exponential control of diagonal elements to compute entanglement, right? The things like what is the black hole mass are not that, are just diagonal elements, and the calculation of Hawking will work all the way until the black hole is very small. So it depends on which question you're asking.
What is the recent developments in trying to solve the information paradox? They would say that this is not true, right? That there is a breakdown of effective field theory, after page time.
So effective field theory, the calculation of things like entanglement between a system with many degrees of freedom and the radiation, that is not something you can compute with the effective field theory. It's sensitive to things which are very, very small. And if you want to take those into account, well, then you need to do more sophisticated stuff. But just for the basic things like what is the effective field theory is good at computing the diagonal entries of the density matrix, which control things like the mass of the black hole, not good at the diagonal ones. But in the diagonal ones, it does work all the way to the small thing. If you're still worried, take the B0 to be even bigger, and then try to make the argument until the page time. Right? More questions?
Are you saying that the entanglement entropy cannot be trusted because
No, I'm just saying that if you're looking at things like entanglement, right? If you have some density matrix, right, and you change an off-diagonal entry of the density matrix by something like e to the minus s, some correction that would be very hard to compute in the effective field theory, that can change the entanglement up to other one things. So that's what I'm saying. More questions?
And you know the particle mass is still in Planck and not growing up, in Planck plus 1 over 1 plus b plus 1 or something similar.
Right. So the assumption here is that the Hawking calculation is valid to some length scale. Could be bigger than Planck. I'm assuming it to be Planck for making the argument simple. But if so, I can run the same argument for every charge, right? And it's always going to make it to whatever that scale is, and Planck or whatever it is.
Because you're saying that black hole is the same, solution is the same,
Yeah, exactly. And there's some regime of validity, and I run the calculation up to the endpoint of that regime of validity.
Can I get away off if there's some fastballs? If you see that there's no black hole and you have some structure that horizon coming from string theory, and then you never get black hole.
That's a...
Then you will kill fastballs.
Sorry?
Then you will kill fastballs.
Well, no, I would kill fastballs in theories with global symmetries. Yes, I don't think that, to the extent that Hawking calculation works, I don't think it would change too much, right? If you're telling me, look, actually, because of fastballs, if I take a black hole of mass m, there's a breakdown of effective field theory which is dependent on the black hole mass, then that could be a loophole. Yeah. Okay? Anyway, so you have these infinitely guys. So you get infinitely many stable particles. That's bad. Again, it's bad. It's not something that happens in quantum field theory. Normal quantum field theory, again, something you be complete, something that maybe is like a CFT at high energies, and then as you go down, there's some mass scales and has some particles or whatever, gives you a density of states which is bounded at any energy. Cannot produce infinitely many states. In quantum gravity with global symmetries, however, you actually get infinitely many states of Planckian mass or whatever the mass of this small black hole is. Again, something that doesn't happen in quantum field theory. But this time is way worse than what we found before with the two black holes colliding was like a funny thing. Okay, the cross-section is different. Okay, you form a black hole. But here, it's actually, these guys are much more dangerous at low energies. These guys are called black hole remnants. There's a beautiful paper by Lenny Susskind called Trouble with Remnants, if you want to have a look at what happens with these. And they really can impact anybody doing any kind of physics problem. Suppose you're doing condensed matter physics. And as you are doing a PhD in condensed matter, and somebody asks you to compute what happens when you put the system at temperature T. Okay? Well, you sum over all the states on your system, Boltzmann partition function, and then you say, oh, right, this guy says there's these remnants, so I need to include the remnants. But they're crazy suppressed, right? Because my condensed matter, temperature is like, I don't know, 1 Kelvin, and here is suppressed by the Planck mass. So they don't matter, do they? Well, I just told you an infinite number of them. So they actually matter. So it's going to make your partition function blow up, heat capacity blow up. Everything blows up, okay? It's not just that, okay? They also run in loops, principle. So the idea is that these guys overrun every calculation that you can do in effective field theory. So that means that in any reasonable theory of gravity, which is Einsteinian plus a quantum field theory, so kind of like our universe at low energies, these guys should be absent. They give you trouble otherwise. So there should be no remnants, and since we got the remnants from the global symmetries, this means there's no global symmetries. Okay? Is this a proof? No, obviously not. It's a heuristic argument, has a bunch of loopholes, like for instance, like what happens if the mass of the particles is 0, and there's a bunch of things. But it's a motivating thing that black holes, because of UV-IR mixing, can lead to this consequence at low energies. And indeed, I told you that Swampland things, the way you go about them is you try to find some general argument, and then you check, is this thing true in string theory? And you will struggle to find a string theories which doesn't agree that there's no global symmetries, at least in string theory. Because on top of these arguments that we actually have a proof that there's no global symmetry in perturbative string theory. You can read it in Polchinski's textbook in chapter 18. In holography, and if you restrict to continuous global symmetries, no global symmetries is the same as Noether's theorem for the dual field theory. Okay? So for instance, at least for Lagrangian conformal field theories, this thing can be proven. There's a finer version of this using wormholes and the gravitational path integral that show that symmetries are broken just from gravitational path integral calculations. And again, it is always true in every string theory example. So you see, on one hand, we have the black hole general argument, and on the other hand, we have all the calculations that we get from string theory.
Is it expected to apply to discrete symmetries?
Great question. Yes, it is. For instance, for discrete symmetries, the argument I just made doesn't work. For instance, if you have because discrete symmetries have finally many charge states, right? For instance, if you have a ZN symmetry, I cannot get you infinitely many states, right? It's certainly true in string theory that there are no examples where you cannot argue that any exact discrete symmetry is gauged. It's not in Polchinski, but you can prove it in perturbative string theory as well. And in ADCFT, there's a very long, very nice paper by Oguri and Harlow where they also prove it making some assumptions, okay? The assumptions are called splittability of a symmetry in Rn. It's an assumption, so it's not proven. Nobody has ever found a counterexample of a quantum field theory that doesn't satisfy this property. But for instance, it has not been derived from bootstrap axioms or anything like that. So that's the status. More questions? Good. So there's no global symmetries in gravity. Great. Why should I care? Well, this has actually real world consequences. Remember, we're talking about B minus L is a symmetry of the standard model. So there are no global symmetries in quantum gravity. That means that B minus L cannot remain a global symmetry forever. So there's two possibilities. It's either a gauge symmetry, so that means that there's a fifth force, which we haven't seen yet. Gauge coupling should be very small because we haven't seen it yet. Or maybe it's not a real symmetry. Maybe it's broken. And if it's broken, you should look for processes that violate B minus L conservations, like double beta decay. Okay? So it's interesting from that point of view. Just to flash something that we are thinking about as a research direction right now, you could ask, okay, suppose a symmetry is broken. How strongly is it broken in general? And by thinking about, indeed, scattering processes where you form a black hole, you can sort of extrapolate a natural guess of the size of, for instance, in a 2 to 2 amplitude, how big is going to be the amplitudes that break the global symmetry. And there's a general answer you can write down, which is it's exponentially suppressed, so it's very suppressed, in the ratio of the Planck length and the charge of the smallest black hole in which the global charge fits. Okay? We have some prescription for that. And again, we have checked this prescription, and it gets on the nose the size of the break-in in many concrete string theory examples. So we're quite confident that this is the right answer in general. And notice that you can, for instance, if the size of this charged object is the cutoff of the effective field theory, which is not always, but in many cases is what it is, you can write this like this, where lambda is the energy cutoff of the effective field theory. And again, here you see UBI are mixing. In field theory, if I have some UV physics on some scale lambda, as I make lambda bigger, the effects at low energies become more and more suppressed. Here it goes the other way around. You make lambda bigger, and this thing, the breaking of the symmetries, becomes stronger and stronger and stronger. So certainly, again, something you would not get from quantum field theory. We can also use this idea there's no global symmetries in theories with extra dimensions and with lots of supersymmetry to put very strong constraints. Sometimes we can rule out even entire quantum field theories, assuming supersymmetry, and let's say that you are in more than 6 or 7 dimensions. That's a whole interesting thing, but it's a different story from what I'm telling you today. Yes, please. So lambda is, so the break-in is exponential in the size of the smallest black hole that can eat the global charge. In many examples, you can make charge objects which are point-like in the effective field theory. So then the size of that black hole is the cutoff of the effective field theory. Okay? So you can write it like this. If you know more about the theory and you know there's a UV cutoff, you can replace the formula with that, and the break-in is less suppressed. So depending on how much you know about the theory, you can get a better or a worse bound. Does that make sense? Yeah, okay. Good. That's the no global symmetries conjecture. So now you're all Swampland experts. Because indeed a lot of the Swampland logic follows from this. And if you have been thinking about no global symmetries, tells you, okay, global symmetry is bad. Gauge symmetry, fine. This immediately suggests a way to cheat. Say, okay, fine. This guy is telling me that I should never have global symmetries. If I want to mess with him, what I'm going to do is, okay, I'm going to gauge the symmetry. So I'm going to introduce a gauge field coupled to it, but the gauge coupling is going to be 10 to the minus, I don't know what I put there, 10 to the minus a million, right? for all intents and purposes, this is a global symmetry, right? In physics, there should never be the case that there's a statement that, it's not invariant under a very small deformation of the theory. So what happens here? Indeed, if the swampland is any good, it should do something about this. So what can it do about this? Well, let's keep thinking. So when the symmetry was global, we had troubles with us having, having these remnants. When the symmetry is gauged, that means that there's a long-range field coupling to the charge. When I try to collide the particles to form a black hole, I form a black hole which has an electric field coming out of it, because the particles that I threw in have electric field lines. So instead of a remnant, what I get is an extremal Rayleigh-Nordström black hole. So it's a charged black hole. The evaporation now doesn't go to Planckian size. You can follow Hawking's calculation, and it goes to sort of like the extremal black hole. So in a theory where the gas coupling is very small, we don't have remnants, but we have these Rayleigh-Nordström black holes. So maybe those are problematic. What can we do to make them decay? Well, let's look at the near horizon region of the black hole. So let's take the black hole. You see I draw a little square here. So we're going to zoom in. And so in that near horizon region, it's like there's a constant electric field, because I just zoomed in, and so the electric field is basically constant. Now, what would it mean that the black hole decays? Well, the black hole has this electric field, so if I somehow am able to get rid of the electric field, that's like the black hole decaying. Well, how do I get rid of an electric field? If you have a capacitor with an electric field, one way that the electric field can disappear is if there's charged particles in the theory. If there's charged particles in the theory, they're going to be pair produced by the Schwinger effect, and they're going to start screening the electric field. So you could imagine there's some charged particles that get produced here. One falls into the black hole, and one escapes to infinity. And so these particles, if the theory contains electrically charged particles, then they're going to discharge the black hole. Well, sure, that is true. But you should also make sure that in the process of the pair being produced and one particle being emitted, you satisfy conservation of charge and conservation of energy, right? So the charge and energy of the initial guy plus the final guy should be conserved. And it's a simple kinematics problem. You can work it out. If you want this to happen while the black hole remains extremal or subextremal, turns out that this kind of decay is only possible if the mass and charge of the particle we introduce to this charged electric field satisfies some inequality. That is, mass is less than the gauge coupling times the Planck mass. Okay? This is our second Swampland constraint. It's called the weak gravity conjecture. It's called the weak gravity conjecture because the mass being less than this is precisely the condition that between two particles of the same size, the electric force beats the gravitational force. Okay? So, first thing we did in this talk, we were checking that this is satisfied in the real world by the electron with a huge margin to spare. So the weak gravity is correct. We postdicted a simple fact about the electron. But that's not all the evidence there is. There's a lot of more evidence. It's certainly true in every string theory compactification to date. And that is a lot of evidence. Lots of evidence. It's proven in perturbative string theory. You can prove it in perturbative string theory. And some versions of the statement you can prove with ADS-CFT. There's been also many works thinking about it in terms of scattering amplitudes. So it's a statement that, again, has a lot of evidence, both from general arguments and from string theory compactifications. And there are many versions of this, including, for instance, for extended objects. In string theory, you don't only have particles, you can also have branes and stuff. So they also satisfy a version of the weak gravity conjecture. And even to instantons. Okay, so these are Euclidean objects that have to do with scalar potential. And this can be used, have been used, to put constraints on inflationary models. Okay, so again, this is of relevance to effective theories of interest. Notice that again, this is exactly the kind of thing that you would expect for from Swampland, in the sense that it's a constraint on the effective field theory. For instance, if the gauge coupling is very small, it's 10 to the minus a million, it's telling you that the mass of this particle is very, very light. Okay? So it's telling you something that you would not have guessed from quantum field theory. Okay? So questions about the weak gravity? Okay. So I told you this weak gravity conjecture is true in every string theory example. But in fact, if I for a moment forget about black hole arguments and I just ask what is true in string theory compactifications, turns out that something a lot stronger is true in most string theory examples. It turns out that in string theory you can actually get couplings like this. You can find compactifications, string solutions, where the couplings are tiny like this. But when that happens, you find not just one particle whose mass is less than its charge. You find a whole tower of particles. You have infinitely many particles, or I guess you would cut that at the Planck scale, but so a lot of particles whose mass is less than its electric charge, so they have charge n. So they come in towers like this. So you have a bunch of particles whose masses is related to the charge for any value of n, for any integer. So there's a whole tower of particles. And that means that the breaking of global symmetry in these kind of cases is a lot stronger. In fact, there's so many states in these theories that any reasonable effective field theory in the same number of dimensions breaks down at this scale. And the presence of these towers of states, I told you when the gauge coupling is very small in string theory, there's this tower of states, infinitely many states. That happens whenever there is any small number in a string theory solution, even if it's not a gauge coupling. If you have any number which is tiny, then that's what we call infinite distance boundaries in string theory. We call them infinite distance boundaries because we usually, the models where you can have these gauge couplings be very, very small, they come in continuous families, and so you can sort of like tune it away. And so what happens universally is that when you normalize the coupling that is very small properly, and properly has something to do with the kinetic term of the scalar field that controls this coupling in the Lagrangian. So that's not very important for what we have. But the point is that when you normalize it properly, every time that you have some limit in which there's some coupling goes to infinity, so it becomes very small or very large. I guess I should have put a minus sign here, sorry. Whenever you have one of these limits where a coupling becomes very small, there is some tower of states which becomes light exponentially fast in this coupling. And this is the third Swampland conjecture I want to tell you about, is the distance conjecture. It's not a conjecture about one theory, it's a conjecture about what happens in a family of theories once you make the coupling very, very small. Okay? Questions about this? Yes, please.
In the real world, we don't see particles charge 2 and 3 and 4 being accelerated with electrons. So
Well,
the coupling is quite small.
well, no, but the coupling of electromagnetic force is not so small, right? Like alpha is 137. So who's to say that there's not a tower of things at the, GM Planck for, so that's 10 to the 18.
Where would the next part of the, can you predict something on, let's say this applies and let's say the small unit.
Well, yeah, so that, so that, yeah, but that wouldn't be so interesting, right? Like, for instance, there's other particles, first of all, in the standard model which are heavier and also have electric charges, right? Like, I don't know, quarks, pions. Weak gravity would tell you that those all have to have masses below 10 to the 18 GeV. So it's not a very interesting prediction for that one, but you could try to run the same. Imagine that you have a situation where you say the B minus L is gauged. Then the gauge coupling of B minus L has to be tiny because we haven't observed this force, so it has to be very small. So actually the bound is 10 to the minus 24 or 25, if I remember correctly. And so that is now telling you that there has to be a lot of states whose masses are controlled by are very small, right? Maybe heavier than neutrino mass scale, but a lot of them, okay? So that's an example where you would make something. Yes?
Is the prediction that also the gauge charge of these particles increases with the order in this ladder?
Right, so in cases like this, where the coupling that you're making very small is a gauge coupling, yes, the charge increases as you go up. But my point is that this happens more generally, is whenever any kind of coupling in effective field theory becomes very small, okay? More precisely, you need to have an infinite distance boundary in the moduli space. So you need to have a scalar field with kinetic terms. So, but for the general picture, that's roughly what happens. More questions? Yes, please.
Your previous transparency.
Yes.
I've seen that the previous, the N. The N in Z.
Yeah.
Will be negative.
No, you spotted a typo. Thank you. Should have been positive. Well, I mean, the charges can be both positive and negative. There should have been an absolute value there. Thank you very much. Yes. Anyway, this is the distance conjecture. Notice there was a change of pace in the talk. I was always telling you, oh, there's a black hole argument, blah, 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 this is possible. Oh, look, it's true in string theory. And for this conjecture, I just sidestepped that completely. So even though the distance conjecture has a lot of evidence in string theory, there's lots of proofs, like some of them, for instance, for 16 supercharges done recently by people here. This conjecture has no black hole argument behind it. We're trying to get something like that. But maybe, for the time being, we think of this conjecture not so much as a general property of quantum gravity. It may very well be. We're trying to see if that's the case. But maybe we can just think of it as a general property of string theory. I think that's fair. It's really true in every example anybody has ever explored in string theory. Well, in fact, since now we're just, so I know switch gears, so most of the talk was about general features of quantum gravity. These last 5 minutes are really about string theory. And since I am doing string theory, I might just use all the information I have available in string theory. So in string theory, whenever you have one of these limits when the coupling is very small, you can ask what happens in the limit. You know, there's a tower of states, but these states you should be able to understand from the point of view of string theory. And indeed, in every example ever found, the nature of this tower of states that you get in the limit is just that it's a Kaluza-Klein tower. Anybody here not familiar with what is a Kaluza-Klein tower from an extra dimension? Good. So just to view it quickly, what is a Kaluza-Klein tower? If you have a theory with extra dimensions, let's say you have a theory with 5 dimensions, let's say you have some scalar field S, which depends on space and time, and let's say that the 5th dimension is periodic, okay, so it's like a circle, then you can decompose this scalar field into Fourier modes, like this, and then you see that the Fourier modes effectively, so the full scalar field depends on 4-dimensional coordinates and the 5th-dimensional coordinate, but it's equivalent to this tower of 4-dimensional fields. And if you just plug this in ansatz in the Lagrangian, you will find that these fields is an infinite tower of fields with any n. Here the n can be positive or negative, but their masses, and now I should have put an absolute value again, are there's a tower of states whose masses increases like this. So this is the basic mechanism how you get these towers of states in string theory. When you do Kaluza-Klein, this is called a Kaluza-Klein compactification, you get these towers of states from extra dimensions, and you get these towers of states. So this is sort of like the physics of the distance conjecture in string theory, in all limits below 10 dimensions. So if you take all of this seriously, it suggests that if there is a very small coupling, come on, that means there's a large extra dimension of some sort. That seems to be the case generically in string theory. Okay, so let's apply this logic to our own universe. Okay, what is the smallest coupling that we have measured? We've measured lots of small couplings, right? For instance, like mass ratios, like we just saw the electric force. So the rate of the electron mass to the Planck scale is very small. What is the smallest that we've measured? Neutrino mass is very small, even smaller. For instance, neutron mass in Planck units, right? That's 10 to the minus 28 or something like that, but even smaller. I see Joseph making like this. Indeed, this is the correct answer. The cosmological constant. We have measured vacuum energy whose size in Planck units is 10 to the minus 122. And so this is the smallest coupling. So if that's true, and we've sort of like applied this logic, we would expect maybe there's some sort of like a large extra dimension. Okay, so fine. Let's imagine let's say there's just one large extra dimension. What is going to happen generically? Well, one thing that happens generically in string theory, but also in field theory, is that if you have a large extra dimension, you get a vacuum energy, which is sometimes called Casimir energy, which goes like this. Goes like 1 over the radius of the thing, of the extra dimension to the 4th power. This is fixed by dimension analysis. This is an order 1 coefficient you can compute. So okay, let's pretend that this contribution is there, because after all, what I'm trying to do is to try to collide observations with what is generic in string theory. So if I do this, fine, there may be some other contributions to the vacuum energy, but unless I fine-tune them, okay, it's going to tell you that this thing is going to be roughly of the same order of magnitude as the total vacuum energy. And if that is the case, I can use this formula to invert and get a lower bound on the size of the extra dimension. Okay? So if I just follow this logic, just from extrapolating the distance conjecture and declaring that the smallness of the vacuum energy means that I am in one of these infinite distance boundaries, okay, this is a bunch of ifs, but with the ifs comes a very nice statement. You essentially get that there is one large extra dimension of roughly micrometer size, which is a scenario that we dub the dark dimension for some reason. And this is just a version of large extra dimensional models, which has a different scale and motivation. So in ordinary large extra dimensions, you try to connect the higher dimensional Planck's mass to the electroweak hierarchy. And here you connect to the cosmological constant, to the vacuum energy. And there's been a lot of activity in this scenario the past few years. People have been connecting to dark matter, to particle physics, or to dark energy itself. But the clearest prediction it has is indeed that you have an extra dimension of roughly radius micrometer sized. So this leads, of course, to experimental prediction. The experimental prediction is that if you're able to measure gravitational force between two like particles at, let's say, length scales bigger than 1 over r, it's going to go from 1 over r squared to 1 over r cubed, which is the gravitational force law in 5 dimensions. Okay? So the current experimental bounds are 30 micrometers. There's a group in Vienna by Armin Sayegi where they are doing some experiment that will lower this to 10 micrometers. So it's roughly at the scale where you would maybe start seeing this. So that's an interesting thing. Okay, so what I did in this last part, I took these Swampland conjectures and I extrapolated them. Okay, extrapolated them and tried to confront with observations, and this is what comes out. So it's an interesting scenario with a concrete prediction, which is verifiable in the near future. So with this, I get to the end of the talk. There's many more things that I would have told you about. Like Swampland is something that has exploded in the last 10 years, and there's been a lot of work that, of course, I didn't cover. So there is, for instance, this thing is called the Festina lente bound. There's something called dynamical coverdism. We also have the gravitino mass conjecture. We have the species bound. We have nobody, no SUSY idea should be in the Swampland. Euclidean wormholes, the gravity conjecture, neutrino masses, repulsive conjecture, coverdism conjecture, bubbles of nothing, convexity of the operator spectrum, no de Sitter conjecture. There's many things. There's even more things than this. And so if you're curious, just come to talk. Unfortunately, I can only be around today, but I love to chat. So if you want to chat at any point, you know where to find me. And if you're more interested, you can also maybe join our bi-weekly online seminar series. So here's the link for you to join if you want. So the take-home message is very simple. Quantum gravity gets you non-trivial constraints at low energies that we are only beginning to uncover. These are some reviews on Swampland. And so the sky, you might not worry, the sky might not fall on your head. That's maybe not going to happen. But a tower of extra-dimensional states just might. So with that, I finish, and thank you for your attention.
Can you argue that there is just one large extra dimension and not 2, 3, or?
Yes, that I skipped. You need to check every case. So from the point of view of the distance conjecture, or this kind of things, indeed there's limits where there's one extra dimension of the compacted or 2 or 3 or 4. Okay. So here, what sort of like kills you is the fact that you know its size because it's related to the vacuum energy, and there are bounds on extra dimensions. So you cannot have, let's say, 3 or more extra dimensions that large. It's experimentally ruled out. Okay. So the one case which is safely within bounds is 1 extra dimension. 2 extra dimensions is marginal, and in fact, there's been some recent discussion in the literature. Could it be there's 2 extra dimensions?
I mean, is there an assumption that dimension is a circle? Is a collapse an extra dimension?
No, that doesn't matter too much because imagine take a Calabi-Yau, you decompactify. The density of states that you get is the same as, let's say, if you decompactify a torus, is controlled by the dimensionality that you decompactify into. It's this Weyl formula for the eigenvalues of the Laplacian, for instance. So it doesn't matter. Of course, you could, maybe you can move the contours and order one thing by assuming, no, I have a Calabi-Yau, which is blah, blah, blah. But generically, bounds don't change.
I mean, you don't have one cycle in Calabi-Yaus, so
yeah.
Like, shouldn't it be 2 dimension, which would be large if you
Well,
have a Calabi-Yau?
no. So what would it mean? Imagine there was a Calabi-Yau limit. So you're right that Calabi-Yau has no 1 cycles, or at least not. Doesn't have 1 cycles. So what would it mean, for instance, if the space was a Calabi-Yau? It might not be a Calabi-Yau, but if it was a Calabi-Yau and it decompacted 1 extra dimension, you would imagine the Calabi-Yau, okay? And the Calabi-Yau does like a potato-like deformation like this, right? So indeed, for instance, the metric that I'm putting here is not the Ricci flat metric. Maybe there's fluxes, maybe there's some other stuff, but it would be something like that, okay? That being said, in string theory, most of the examples of the compactification with, let's say, 1 extra dimension, they do include like a factor of an interval or an extra circle, so that's the more common thing. I'm just saying that, you could imagine a metric for a Calabi-Yau that would do that as well.
Thank you.
Thanks for the talk. So I'm curious, one of the kind of concrete challenges when you're trying to build extra dimensional models from string theory is stabilizing all the moduli, in particular volume moduli. So in these dark dimension scenarios or anything,
No.
What insights do you have on
this scenario is Fino. It's a Fino scenario, right? So indeed, I am ignoring a bunch of pretty serious problems. You were talking about moduli stabilization, and indeed that's tough. So for instance, in string theory, right, that you would have like many light scalars, they would give you 2 field forces, and you sort of like wanna get rid of those. There are models, for instance, where you can stabilize all the moduli, but there's even like there's a much bigger problem here, okay, which is I was telling you that in almost, let's say, with large extra dimensions, there's one contribution to the vacuum energy, which is the Casimir energy, and I was using that, right? But I didn't explain to you, and indeed the scenario doesn't address why the vacuum energy is so small in the first place, right? For instance, in a scenario with a large extra dimension, the simplest scenario you can think is like there's the extra dimension, and then there's like a brane where the standard model fields live, okay? So the smallness of the vacuum energy in that picture gets mapped to the smallness of the tension of that brane, okay? Why is it so small? I didn't explain. And if you ask me, that's the even bigger problem that nobody's really addressing in string theory. That's the cosmological hierarchy problem, because the tension of this brane is going to be affected by loops of, let's say, electrons, which would naturally make it big, right? So not everybody, I mean, most people are not addressing that. Because it's a very tough problem, but I think it's also like a very important problem. There was a nice paper by Xuxa Parameswaran, Marco Serra, and Emilian Dudas, where they found some scenario where effectively the corrections to the tension, they vanish at 1 loop. So that's an encouraging step. Of course, you need a lot more than 1 loop to explain this. So that's even the more important question, I would say.
And just in terms of kind of thinking about the lessons from string theory in terms of what type of bounds, I mean, could you imagine that there actually could be a bound from string theory that says like the modulus has to be lower or lighter than a certain threshold or something like that? Would you expect something like that to come out from these Swampland conjectures?
That's there's, for instance, in the context of ADS, like compactifications with negative vacuum energy, which is not the real world, but still an interesting playground. There are statements like that. People have proposed statements like that. The masses of the model cannot be very high. It might be possible, you know, there's an interplay between Swampland and things that you can get just from thinking about like causality and iterative scattering amplitudes and stuff. So for instance, something that some people have discussed sometimes is like, maybe you have like some theory with a large extra dimension. You could maybe give a bound on, let's say, the mass of the volume modulus, just from demanding that propagation of signals in that internal space is causal. So, you know, things cannot get here to here faster than the speed of light. So that has to do with the Kaluza-Klein models I was telling you on the masses of things. Maybe it's all related. I think that's the more concrete idea that I've seen mentioned that would do something like that.
No, I was just wondering for cosmology. So, you know, we have the normal inflationary scenario, or you have some field rolling slowly and, you know, with some small coupling constant and not coupling to too many things. This kind of vanilla cosmology scenarios, I mean, what's the consequence? I mean, if the Swampland conjectures are correct, I mean, you know, are they all trash, or, you know, what's going on with the inflationary? Because, you know, there, you know, it's exactly, you have the fine tuning, and, you know, this fine tuning seems to be exactly the one you are ruling out with these reasons.
Yes, so one thing that we can say kind of like pretty solid, I mean, I didn't have time to cover everything, unfortunately, but one thing that we can sort of like say, for instance, for models of inflation, is that, so in inflation you have the scalar field has like a potential, right, it's like a flat slope, and it goes on for long. So for instance, simple models of inflation, if the scalar field rolls over for a field range which is bigger than 1 Planck mass, or much bigger, you get cosmological signatures like tensor to scalar ratio, which is observable, which we haven't measured yet. In many models of inflation from Swampland principles, you have an upper bound to this field range, okay, which is of roughly 1 Planck. So that would mean you should not see a sizable tensor to scalar ratio. This also comes from distance conjecture, because if you have the scalar field is moving this large field range, right, you know, then I'm telling you that tower of states comes down, and that's invalidating the effective field theory. That is a bit harder to argue rigorously, because you could say, well, maybe the states come down, but they don't affect the effective field theory. Maybe the effective field theory is somehow protected by it. So that's a bit harder. Concrete, you make a model, the more precise you can make the bounds. So for instance, with the weak gravity conjecture, models of natural inflation, you can argue that the field range is not going to be Planckian, or much bigger than Planck. Models where you have like a monodromic axion, you can sort of do the same. If you want to have a general model that you're going to put a general bound, you have to use the distance conjecture, as far as I know. So you can certainly say that. Then, of course, there's all the other problems, like there's all this fine-tuning. How do you explain that? Yeah. There's another Swampland conjecture that I mentioned briefly that you know very well, of course, which is like here is the de Sitter conjecture. So that's a conjecture relating the scalar, essentially putting bounds on the gradients of the scalar potential in the moduli space. So that will also be in trouble with inflation. And it would be in trouble with having a cosmological constant now. It would mean that the cosmological constant now actually has like some small time dependence, which I don't know if everybody's aware, but there's like this experiment called DESI, which is seeing hints of that. So that's, I think, that's another very interesting thing that I didn't have time to cover. Thank you.
Okay, I don't see any further questions, so let's thank again Miguel.
Thank you.